and welcome to this video going over Lesson 2.1 Inductive Reasoning and Lesson 2.2 Deductive Reasoning. In this video, we are going to talk about the difference between inductive and deductive reasoning and how we can use both types of reasoning to make conjectures and theorems. So let's get started. Starting with inductive reasoning. Inductive reasoning is the process of observing data, recognizing patterns, and making a generalization known as a conjecture. For example, if I had a class where the majority of students had blonde hair, I could make a conjecture that all of the students in Willow Glen High School mostly have blonde hair. Now, this is a generalization based on my one class. I observed some data, I recognized the pattern in my classroom, and I made an overall generalization. Now, my generalization might be true or it might be false, but I didn't actually prove it. All it was based on was making observations and recognizing patterns. So what we are going to do is we are going to look at the following patterns and use inductive reasoning to make a conjecture about what the next two terms are. So based on what is right in front of us, we are going to try to decide what the pattern is using inductive reasoning and determine the next two terms. So I have A4, C8, E12, and G16. So it looks like every other term is a letter, and it looks like I'm skipping letters. So I did A, which should have been B next, C, which should have been D, E, F, G, H. So I know the next term is going to be I, because it's every other letter in the alphabet. And then it looks like the numbers are going up by 4s. I have 4, and then 8, and then 12, and then 16. So the next number would be 20. So based on the pattern in front of me, my conjecture is that the next two terms are I and 20. In my next pattern, I have 3, 9, 27, 81, and 243. So to me, it looks like I am multiplying by 3 to the previous term to get the next term. 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81. So what I'm going to do is I'm going to multiply 3 to 243, and I get 729. And then if I multiply by 3 again, I get 2,187. For the next pattern, I have 1, 1, 2, 3, 5, 8, 13. Now this one's really tricky. There's actually a name for this pattern. It's called the Fibonacci sequence. And if you took some time to really look at it and make your best guess, you get the next term by adding the two numbers that came before it. So for example, to get 2, I added 1 plus 2. To get 3, I added 1 plus 2. So in order to get the next term, I need to add 8 plus 13, which is 21. And then to get the term after that, I am going to add 13 and 21. And that will get me 34. Last one, it says draw the next figure in the sequence. So it looks like I am rotating this triangle 90 degrees clockwise each time. So if I'm going to rotate it 90 degrees again, it is going to be facing this way, and the shaded part is going to be on top. And so there I demonstrated using inductive reasoning. Inductive reasoning is observing data, recognizing patterns, and making a generalization known as a conjecture. So these conjectures that I made, determining the next two terms, were just based on the pattern put in front of me. What we're going to do next is talk about deductive reasoning. Deductive reasoning is using rules of logical reasoning to convince someone that a conjecture is actually true. So think about the scientific method. If you've ever been in a science class, you always start with the hypothesis, and that hypothesis is an educated guess. It could also be known as a conjecture. It's based on patterns and observing data. But then you actually perform an experiment to actually prove your hypothesis is true or false. That second part is deductive reasoning, actually using rules of logical reasoning and evidence to prove a conjecture is true. And so in order to prove a conjecture is true, we need a proof. We need a series of logical reasoning and evidence to transform a conjecture into a theorem, and that's called a proof. And then once a conjecture has been proven, it is called a theorem. So let's see an example of using deductive reasoning. Some rules to get started though. An even integer is an integer that has a remainder of 0 when it is divided by 2. So anything that's able to be divided by 2 perfectly is even, such as 2, 4, 6, 8. And any integer that has a remainder of 1 when it's divided by 2 is odd. So for example, 1, 3, 5, 7, 9. So we're actually going to start with some inductive reasoning first. Making conjectures about the sums of even and odd integers. Since we're only making conjectures, this is inductive reasoning. It says calculate the sum of some pairs of even integers. Using the examples you find, make a conjecture about the sum of 2 even integers. So let's add some even integers together. 2 and 4 are both even, and if I add those together, I get 6, which is also even. 8 and 10 are also both even. 8 plus 10 is 18, and 18 is even. I could also add 6 and 12. Those are both even integers. 6 plus 12 is also 18, and 18, once again, is even. So based on these 3 examples, I notice that every time I add 2 even integers together, I get an even integer as an answer. Now, this is using inductive reasoning because I didn't prove this for all sums of pairs of even integers. This is only based on 3 examples. My next example could disprove this conjecture, but based on the examples that I have in front of me, I'm going to make the conjecture that the sum of 2 even integers is always even. Now, once again, this was just based off of 3 examples, which means this is an example of inductive reasoning. I didn't actually prove this statement. It's a generalization based on some examples. Let's try this again. Calculate the sum of some pairs of odd integers. And we're going to do the same thing. We're going to make a conjecture based on the results that we get. So 1 and 3 are both odd. And if I add 1 plus 3, I get 4, which is even. 5 and 7 are also both odd. If I add those, I get 12, which is also even. 9 and 11 are also both odd. And if I add those, I get 20, which is also even. Now, once again, I'm only witnessing 3 examples. I could do this infinitely, but since I did not prove it for all pairs of odd integers, and I'm only basing this conjecture on some examples, this is an example of inductive reasoning, making a generalization based on a pattern or based on examples. But my conjecture is going to be that the sum of 2 odd integers is always even, because every time I added 2 odd integers, I got an even integer. Now let's do this one more time, but now let's add 1 even integer and 1 odd integer. So for example, 1 plus 2. 1 is odd and 2 is even. 1 plus 2 is 3, which is odd. I could also add 4 and 5. 4 is even and 5 is odd. 4 plus 5 is 9, which is odd. And one more. 10 is even and 11 is odd. 10 plus 11 is 21, which is also odd. So my conjecture, based on these three examples, is that whenever we add an even integer and an odd integer, it will always come out odd. So that was an example of inductive reasoning, making some generalization based on just a few examples or recognizing a pattern. What I want to do now is turn these conjectures into theorems. And so I need to actually prove that these conjectures are true using deductive reasoning, using logical reasoning to represent all integers, not just a few specific examples. So we are going to use deductive reasoning to prove my conjectures are true. So in question 4, it says use the expressions 2p and 2m, where p and m are integers, to confirm the conjecture about the sum of two even integers. So p and m are any integers, 1, 2, 3, 4, 5. And by multiplying by 2, we confirm that they're even. So 2p and 2m are two even integers. And we set up here that the sum of two even integers is always an even integer. So let's see what we get when we add these two together. 2p plus 2m. Well, since one has a p and one has an m, I can't combine them. But since they both have a 2, I can factor out the 2. 2p taking away the 2 would just be p. And 2m taking away the 2 would just be m. And notice what I'm left with. P plus m will still be an integer. And it's an integer multiplied by 2. Any integer multiplied by 2 is even. And so what I just proved is that no matter what two even integers we add, it will always come out even. This is deductive reasoning. I wasn't just basing this on a few random examples. I proved this for all integers. And so by using these variables to represent all integers, I proved that the sum of two even integers is even. Number 5 says use expressions for odd integers to confirm the conjecture about the sum of two odd integers. So we set up here that if we ever add two odd integers, it always comes out even. Let's see if this is true. Notice how in 4, I used the expressions 2p and 2m to represent even integers. To represent an odd integer, I'm going to say 2p plus 1 and 2m plus 1, where p and m are integers. "2p plus 1 and 2m plus 1 represent odd integers because if I take some integer, like p or m, and I multiply by 2, and then I add 1, it guarantees that that integer will be odd. So I'm going to add these two odd integer expressions together, and I can combine like terms. I have 1 and 1, which would be 2, so I have 2p plus 2m plus 2. If I factor out a 2 again, I am left with p plus m plus 1, which would be an integer. And notice how once again I have the form 2 times some integer, which means my answer will always come out even. And so we just use deductive reasoning to prove that the sum of two odd integers will always come out even. Let's try this one more time. I want to prove my conjecture about the sum of an even and an odd integer. I'm going to use 2p to represent my even integer and 2m plus 1 to represent my odd integer. I can factor out a 2 from the p and the m, but then I have the plus 1 left over. And now notice this form. I have 2 times some integer, and then a plus 1 left over. This is the form of an odd integer. And so we just proved that if we add an even integer and an odd integer, our answer will always be odd. Now I know some of this deductive reasoning might have been confusing with all of the integer talk and all of the variables, but I hope you see the difference between inductive and deductive reasoning. Inductive reasoning makes a generalization based on just a few examples or recognizing a small pattern. Deductive reasoning, on the other hand, actually uses facts and logical reasoning to actually prove that a conjecture is true. So notice how I used variables to represent all integers. I wasn't focused on just a few examples. I was trying to make the case for all possible integers. Please let me know if you have any questions about the difference between inductive and deductive reasoning, and I will see you in class.